Okay, guys. We're off to a slow start, but we are off to a start. They can. You just don't get the respiratory stuff. So guys, ball's in your court. To get the conversation started, but we are going to get the conversation started. Guys, we're looking today at reviewing the things that affect reaction rate that are not concentration. So, ball's in your court. What questions do you have that you'd like to look at? Because if you're only just now reaching for your homework going, oh yeah, no. You guys all okay? Ronnie, go ahead. Just a sec. Yes. So maybe we need to read the question because we understand that surface area is a big deal, right? But is the question specifically in the context of a catalyst? Okay, so most heterogeneous, okay, so let's talk about heterogeneous catalysts. So heterogeneous catalysts are surfaces upon which reactions are favored, right? And so if it's a surface, we know that the more surface area there is, the more likely you will have a successful interaction that'll cause the reaction to happen more favorably. And so when you take something and grind it up or make it smaller, you're literally exposing more surface area, more active sites, increasing the likelihood that the thing's going to work. A great example of this is in your car. I don't know if you're familiar. There's this thing in your car called a catalytic converter. And literally, it's full of these little ceramic pellets that are coated in platinum. And the platinum actually takes the exhaust gases from your car and it causes them to more completely react with oxygen, meaning that you're no longer releasing carbon monoxide and things like that, but carbon dioxide. But what they do is they take really small pellets and coat those with the platinum because that creates more surface area. So the smaller the objects, the more surface area you've got. Is that okay? Okay. Emma, were you going to say something? What about it? Oh, was that actually? Oh, so there it is. So catalytic converters. So the problem is that especially when we first start our cars aren't warm, obviously. And consequently, the combustion that takes place inside of our cars where we're burning hydrocarbons, gasoline, but there's also contaminants in there that contain nitrogen. And when these things burn, if they don't completely react with oxygen, we end up with carbon monoxide and other deadly gases being produced. And so there are these things in our cars called catalytic converters. So you've got the engine, you've got the tailpipe, and you've got the muffler. Between the engine and the tailpipe, there's another thing that looks like a muffler. It's just a bulge in your exhaust system, and it's called a catalytic converter. And inside there are all these little pellets. Does it mention that it's platinum? I don't know if it does. But anyway, there are all these little pellets that actually grab a hold of these exhaust gases and cause them to combust more completely, making them less dangerous. Did you guys know about what happened up in Canyons District several years ago? So literally these catalytic converters have these little pellets that are coated in platinum. And guys, platinum is more expensive than gold. These catalytic converters are really expensive. And Christmas break, like 5 or 6 years ago, a bunch of idiots broke into the bus barn up at Canyons District, and they cut all the catalytic converters out of all the school buses. and then probably took them and melted them down and got the platinum and sold them for drug money. But so when all of the bus drivers came back to start their buses, they sounded like Harleys because they cut through so the buses couldn't run that day because somebody broke in over Christmas and stole all the stole the catalytic converters to get the platinum out, which is pretty slimy. So anyway, Emma, that's what you need to know. Yeah. Yeah, so like what are you going to see on the test relative to catalysts? So one of the things that you'll see is they'll ask you to identify whether it's homo or heterogeneous. That certainly is fair game. Another thing that you will see is if it's a homogeneous catalyst, and think about that for a second. So homogeneous is not a surface, right? So a homogeneous catalyst many times is a substance that is consumed by one step in a mechanism, and then it's produced as a product in a later step in the mechanism. And so one of the questions they like to ask is this substance a catalyst or an intermediate? And so thinking about that, you'll see that, remember, intermediates by definition are created and then consumed. Catalysts by definition are consumed and then created. You're going to see the lab that we're going to set up today. That will be the case, that it'll be a homogeneous catalyst and it goes in as a reactant and comes out as a product. Another question that you'll see a lot on the test about catalysts is they will actually draw for you it seems silly, but they'll draw for you series of reaction energy diagrams. And so maybe they'd give you one like this, and then they would give you a series of choices that says which one of these choices represents a catalyzed version of this reaction. And what you would be looking for is the reactants are at the same place, the products are at the same place, but the hump is lower. Whether it's a multi-step hump or not, the reactants and products are in the same place. It's just the hump is dropped. And they'll ask you which one of these curves represents a catalyzed version of the reaction. So you'll see that as well. So guys, other questions or things you want to talk about relative to the homework? You guys okay? Yeah, oh, please. Here, let me go back. Okay. No, let's talk through it. I'm frankly not exactly sure what you're saying. Maybe we should say this to start. Concentration isn't represented anywhere in this graph. So this is energy and not concentration. So let's draw. So here, why don't you draw? Come and show us what you're talking about. Okay. Longer than what? What are you comparing to?
I'm not sure exactly, but I just think like the rate of the reaction.
Okay. So no. Let's play with your idea. So remember that this is energy and not concentration, right? Now you're feeling weird because you're at the board. So this is energy and not concentration. So this doesn't mean create a lot and then create less. This means that this takes a lot of energy to get over this hump. So this is the activation energy, but once it gets over that, it'll have enough energy to get over this and fall to products. So this would...
It all happens in one, like, so they all hit together. The first thing switches if it has the right amount of energy.
Yes.
And then the second one is they don't like break apart, and the new molecules have it.
They could. It depends on the mechanism. So it depends on what the mechanism is, but we can say that this would be the rate determining step. Because it's got the highest activation energy, that would be the rate determining step. Is that getting at what you're thinking? Are you okay now? But do be careful with this idea that concentration is represented in this. It's not. It's energy and not concentration. What else, y'all? Yeah? No, well, sort of. So each hump is a different elementary step in the mechanism, or it could be. If the elementary step has no impact on the overall rate of the reaction, it may not show up, but we can't necessarily say that this is a reaction that happens through one elementary step. There could be other elementary steps that are just masked by the first one. But we can say that if we've got multiple humps, each one of those is representative of a different elementary step. So we know there's at least two. There could be more. There's at least one. There could be more. Yeah, so yes, well, we got to be careful with intermediates because it could actually be another reactant. It could be, well, with an intermediate. So this elementary step could create an intermediate that then reacts with a second reactant and then getting over the hump. So be careful about reading too much into these things. The only thing we can say with certainty is that if the hump is lower, the reaction goes faster, and each hump does represent a different elementary step, but it doesn't represent necessarily all of the elementary steps. Is that okay? Donnie, you were going to take us somewhere. Okay, hold on. So here and 81, second. Go ahead. Oh. Hold on, my computer freaked out and I'm not tracking with you. Sorry. So, do catalysts
affect the overall enthalpy change for a reaction, the activation energy versus
Great, okay.
So obviously it affects the activation energy.
Correct.
But it said it only affects that.
Correct.
So if the activation energy is lower,
yeah.
does that not affect the overall?
Hey guys, do not miss this. They're going to throw this at you on the AP test. Don't miss this. So we talked about this set right here, kind of. It's sloppy. But they gave us an overall reaction, and then they said which one of these other graphs represents the catalyzed version of this. Here's the thing you're looking for. This and this have got to be in the same place. This and this have got to be in the same place. So when you add a catalyst to a reaction, it does not change the energy of the reactants or the energy of the products. The reaction is still starting in the same place and going to the same place. The difference is the height of the hump. So then the question becomes, what in this graph represents the enthalpy change? And that is this. This is delta H. This is delta H, and those have got to be the same. So the enthalpy change doesn't change. So if they offered you something that looked like this, that wouldn't be it, because that's a different reaction. It's not starting and ending at the same place. Yeah, no. So the enthalpy change is literally, remember when we did this back in chapter 5, the enthalpy change is literally products minus reactants. So what is the enthalpy of the products? What is the enthalpy of formation of the reactants? And then the difference between those is the enthalpy change. So it's strictly products minus reactants, no matter how they get there. Yeah, because remember, we've been able to calculate those since chapter 5, and we're just now talking about mechanisms. So mechanisms don't play a part in overall enthalpy changes. Okay, go ahead. Yeah? Hold on, I got to wrap my head around that. Spontaneous endothermic? Okay, all right.
How is it spontaneous?
Yeah, let's play with it. So a spontaneous endothermic reaction, right? Okay. No, we're not going to dwell on it a lot, but why necessarily would it be? Absolutely, yeah. No, it's an intriguing question, right? But so the idea is this. While yes, the activation energy going in the opposite direction is less, there still may not be enough available energy to get over the hump. Because remember, the thing that's driving this reaction in the first place is not the change in enthalpy, it's the change in entropy. So we've already demonstrated that there isn't enough available energy to drive the reaction. That could also be true of the reverse process. So it could very well be that if the only thing driving this reaction is the entropy change, there isn't enough energy to drive either process spontaneously. And so consequently it wouldn't happen. Because also remember that it's not this energy that is represented in our endo or an exothermic, it's this energy change, right? And so what we're looking at now is something that is exothermic, but it may not be exothermic enough to drive the process. Is that okay? And again, the thought is that we come back to entropy, because entropy would, as you stated it, would be the driving force. Anything else, y'all? Go ahead, Ronnie. 59B. Go ahead. Yeah, and it's not a must, because here, let's do this. This is going to be grossly exaggerated. Imagine if we had that reaction. This could be like 1,000 million degrees, and these things could be running into each other like banshees, and nothing could happen simply because they can't get over the hump. Right? And so that's whenever you hear the word must or always or never, you know that they're talking you into a corner. So could it? Sure. Must it? No. Because if it's got a huge activation energy, you could have a huge collision factor or whatever, frequency factor, but the reaction may not happen very quickly, because that's really what K is a function of. It may not be happening very quickly simply because it can't get over the hump. Is that okay? What else, y'all? Great questions. Great way to start the day. Y'all good? Okay. So, guys, we have a day today that is going to end up being split in half. The reason is because today we're going to do something that you haven't seen before, compliments of our good friend COVID-19. This was actually in general chemistry, where we ended up in that online environment, and there was no way for me to show you today last year the thing that we're going to share. So guys, normally today what happens is we get through a ton of material, because what I'm about to show you, we're now in chapter 15. What I'm about to show you about equilibrium is super familiar, and all of a sudden you're like, oh my gosh, that makes a ton of sense. I totally get it. And now it makes even more sense because I understand reaction rates. Well, guys, you do not have that common foundation upon which to draw. So we're going to go as slow as you need. We're going to drink deeply of this material. We're going to slow down and do this well. But guys, before we do, we have like 11 million homework assignments to record. And we're going to do that now simply because we do have time. So let me get rid of this. Let me grab a hold of this. So guys, the first one we're going to record is the assignment that we just looked at. So here we go. Braden, were you good? Say it again. No. Matthew. Donnie, you good? Soph? Annika? Ethan? Ishmael? Josh? Diana, you good? Chandler? Isaac? Ellie? Landon, you good? Nathan? Emma? Max, you good? Leslie? Gage? Ronnie? Kaylee? Spencer? Daniel? And Meredith. Okay, so guys, the next assignment that we are going to record, we're going to just go backwards in time. So the next one that we're going to do is the reaction order assignment. This is the one where we were looking. It was day 2 of the unit. Well, hold on. So we've got 2 more assignments to record. Rate expressions and reaction orders, because we already did reaction mechanisms. So the one we're going to do now is reaction orders. It was the 2nd day of the unit. It was the one where we said double this, double that, first order. Okay. All right. Braden, were you good on that one? Matthew. Donnie, you good? Soph. Annika. Ethan. Ishmael. Josh. Diana. Chandler, are you good? Isaac. Ellie. Landon. Nathan. Emma. Max. Leslie, you good? Gage. Ronnie. Kaylee. Spencer.
What numbers was that one?
Can someone help with that? I don't know. So it's the one with 27 and 28 out of chapter 14.
Yeah, so I showed there.
Okay, Daniel. Meredith, you good? Okay, then guys, the last one that we still need to record is the rate expression assignment. That is the first assignment out of this unit. Braden, you good? Yes? Matthew? Donnie? Soph? Annika? Ethan? Ishmael? Josh? Diana? Chandler? Isaac? And Ellie? Landon? Nathan? Emma? And Max? Leslie? Yes? And Gage? Ronnie, you good? Kaylee? Spencer? And Daniel? Meredith? Okay, so guys, that is everything that we needed to make up, so we're all good there. Let me do this really quickly, and we're going to dig in. All right. So guys, changing gears somewhat radically today. Guys, today what we're going to do is we are going to dig into the concepts of equilibrium. Again, I alluded to this earlier, but any other year, we would be gathering around an otherwise familiar thing, and you would all be going, oh, I remember that. And then we would be talking about all these interesting new things that we can talk about this year, and all of a sudden this comes to life in new ways. Well, guys, today we're going to be starting from scratch, although not completely. So, guys, you learned this last year on a screencast, but I could not show you what I'm about to show you because I did not have the ability to embed it in my screencast. So instead what I did is I found a YouTube video. Cast yourself back. It's April. We're just beginning to figure out what this whole game is going to be like. And guys, you watched a video where there was a teacher that had 2 fish tanks. And we had the cups, and they were dumping from one bucket to the other, and they were going up, and they kind of... Okay. Guys, we are going to do the same thing today. Only instead of Tupperware containers or fish tanks, we are going to use 2 graduated cylinders. And then, guys, what I did is I took some water and I dyed it blue so that it stood out in greater relief. And then, guys, instead of using cups or whatever it was that they used to move these things forward and back, we are going to use these glass tubes to move reactants to products and products to reactants. Now, guys, let me set the stage for you a little bit, and then there's some work that you're going to need to do in order for us to get into this in greater detail. So, guys, it goes like this. So this side is reactants, this side is products, and the blue stuff represents all of the elements in this reaction. So literally the blue stuff, which I couldn't say to you last year, the blue stuff is our system. It doesn't matter if this stuff is on the right or if this stuff is on the left. Guys, that is our system. So here's the scoop. Guys, in some reactions, reactants turn into products. And when the reactants are gone, the reaction is over. Guys, what do we call a reaction that fully consumes its reactants, and when the reactants are gone, the reaction is done? Do you remember the name for that kind of reaction? It's called a quantitative reaction. If you don't remember that, you may want to scratch it down. Guys, quantitative reactions are reactions that consume the entire quantity of their reactants. It's a term that you need to know. But guys, there's a whole nother kind of reaction that we need to remind ourselves about. These are reactions that, and we should actually talk about this as well, because I realize you haven't really done this with me. So guys, when we have a quantitative reaction, when the reactants turn into products, which reactant determines how far the reaction can go? The limiting reactant. Guys, if you don't remember that term, that's another term that you may want to include in your notes. The limiting reactant is the reactant that you run out of first. That's the reactant that limits how far the reaction can go. The example that we gave in class is if you light a match, the match is reacting with the air, and thank goodness it goes out when the match is gone and not when the air is gone. Right? Although that is how people die in fires. You know that, right? That in house fires, a lot of people don't burn to death. They suffocate because the fire is consuming all the oxygen in the house. But yeah, in this case, it would be the match. Okay, so guys, we've what's that? Unicorn tears. Or food coloring. I'd prefer it to be Smurf blood. Yeah. But none of that is pertinent to what we're doing, right? Here we go. Okay, so guys, let's now talk about equilibrium, because I'm going to show you what equilibrium is not. So guys, when we represent equilibrium, we talk about a reaction. So this is a quantitative reaction, right? A turns into B. When you run out of it, it's done. Well, guys, now we're going to talk about an equilibrium process. And in an equilibrium process, guys, please do not have the idea that it's this. That reactant turns into product, and then product turns into reactant, and it's not cycling back and forth. Guys, what is actually happening is the reactant turns into product, and all the while, the product is turning back into reactant, and it's cycling on each other. Do we all share that understanding? Okay. So guys, at that point, we need to start putting a finer point on this. So guys, join me here. Are you okay with this idea? The chemical equilibrium occurs when reversible reactions occur at equal rates. So when we hit this point of equilibrium, the forward and reverse reactions are happening at equal rates. But guys, notice that there's two incredible things here, and this is out of last year's definition. You got this in general chemistry. But guys, understand that given what you now know, there's a whole lot of stuff going on here that you couldn't talk about before, like the word reversible. Guys, think about what we know about reversible reactions from what we talked about in chapter 5 and 19. We talked all about reversible reactions. We linked them to spontaneity. We said that they are not spontaneous because they're going both directions simultaneously. We'll talk more later. But guys, now realize this. All of a sudden, this word means so much to you. Because you know that rate is the speed at which a reaction is going. You know that there are four factors that influence it. You know how to write rate laws. Guys, now we can really talk about equilibrium because of everything that you know about rate. So here then is what we're going to do. So when we reach equilibrium, this is further fleshing this out. I don't know if you need to write this down or not. So the idea, guys, is that when we reach equilibrium, the rate at which the products are becoming reactants is equal to the rate at which the reactants are becoming products, vice versa. You good? Okay. So guys, here's what we're going to do. We are now going to carry out this process. Skip down 3 lines and write this really big. We are now going to do this. But guys, here's what I want you to do. Write the rate laws for the forward and reverse processes. Write the rate laws for write the forward process up above, because that's the right pointing arrow, and write the rate law for the reverse process underneath. Write the rate laws for these processes. You guys good? Let's take a look. So guys, here's what we've got, and here's the way we represent this. So we've got the rate forward. So sub F for forward. And the rate forward is equal to K forward times the concentration of the reactants. If you didn't get that for the forward rate law, change it. And then based on that, rewrite your reverse rate law so that it's now correct. You guys okay? So let me catch up with you. Rate reverse is equal to K reverse. Guys, what goes in the brackets here? Products. Because your products, weird thought, right? Your products are the reactants for the reverse reaction. Deep, right? But guys, that is the case. So there's lots of things to be noticed here. So first of all, you'll notice that the rate laws for the forward and reverse reactions are not even similar. They don't even share the same K values. The K values for the forward and reverse reactions are not the same, and then the products become the reactants for the reverse reaction. Does that make sense? Okay, so now guys, I'm frankly not exactly sure how to approach this with you, because normally at this point I'd be working with a group that has seen this before, and we can just launch into this and we can just talk about it. So rather than launch into this and talk about it, what I'd like to do is I'm actually going to do this for you twice. The first time I'm not going to say anything. The first time we're just going to let this flow, show you what's going to happen, and then I'd like to talk with you about it. So guys, this is the way this game is played. Oh, that was right. So guys, when a reaction starts, we've got all reactant and no product. And then guys, when a reaction starts, here's what happens. We've got a bunch of reactant to turn into product. But guys, how much product do we have to turn back into reactant? None, right? And so when the reaction starts, we have a bunch of reactant to turn into product. That's a pretty fast forward rate. But guys, you'll notice we don't have any reverse rate. There's no product turning into reactant. And guys, I need to tell you, there's probably, I'm always pulling at my mask, right? I'm not going to be able to do this and pull on my mask. I'm just going to have to let it slip off my nose. So I'm far enough away that I think we're okay. All right, so we're going to go reactant to product. But now guys, look. Do you see that we now have some product turning back into reactant? And then the reaction continues. Reactant to product, product to reactant. It's kind of hypnotic and a lot harder than it looks. Notice I'm in a good athletic stance, knees bent, which frankly is just about to kill me because I'm still aching from that stupid COVID shot. Yeah, it'll be fun to watch this screencast 5 years from now. What was COVID? So guys, as I continue, and maybe we should even talk about it. Guys, as I continue, eventually what's going to happen? So maybe the same amount of reactant as product? Other thought? I forget you guys don't know. I'm sorry. Hold on, we should start over. I forget you guys don't know. So let me do this. I've never done this with an AP group that doesn't know these answers. So guys, did I show you that the forward tube is bigger than the reverse tube? Maybe you saw that from a distance. It doesn't fit inside the other because I rounded the edges, but the outside diameter of this tube is the same as the inside diameter of this one. So literally the forward tube is larger than the reverse tube. So guys, with that said, let's just talk about it. As I continue to do this, eventually what's going to happen, and Donnie, I heard you say 50-50, that the amounts will be the same. You sticking with that? Because we've already gone past it, right? Yeah. Go ahead, Ronnie. Okay. Yeah, the thing that's interesting is some reactions actually do this. They're called oscillating reactions. This doesn't oscillate, but some do. Because I chose different sizes. And this is, so you're going to see this is important in a minute, and we're going to crack open our books and do some math about those tubes. It's really fascinating. So guys, go ahead, Matthew. Maybe. Yeah, and we're actually going to look at that in just a moment. So guys, let's do this and let's see what happens. And Ethan is exactly right. Again, guys, I forget that you haven't seen this. And maybe if I had asked without showing you what was happening, you would have seen, or you might have guessed that it would stop at 50-50. But when it finally occurred to me that you hadn't seen this before, we'd already gone past it. And then Ronnie brought up this idea of oscillation, that maybe we get to the point where they start moving forward and backwards so that the levels sort of do this. And guys, some reactions do that. I actually did my senior honors project in college on oscillating reactions. The energetics of those things are really interesting, but the reactions that we see will not oscillate. So guys, notice as we do this, the amount of products is going up, the amount of reactant is going down, and as we continue, let me do one more and then we'll get some data. So guys, right now the reactant tube is at 40, and this is at just a hair under 60. I dribbled a little bit, but we did start with 100. So minus the dribble, the law of conservation of mass still works. So now as I continue, I think even from a distance you can see that reactants are still going down, and maybe you can see their products are still going up. Let me stop again and get us some data. So guys, this is at 35, and this is at 65-ish. It's a milliliter under, but 35 and 65. And then guys, let's continue. And as we continue on, let's do a couple more. All right, and this is at 65, and this is at 34. So minus the dribble, 65 and 34. And let me do a couple more. And guys, last one. And this is at 65 and 34, and it's just going to stay. So guys, if I continue to do this forever, what's going to happen inside of those tubes? Going to stay the same. Do you see how what we see in those graduated cylinders is reflected on what's on the board? We have now reached the point where the opposing reactions are happening at equal rates. And as we look at that, we know that they're at equal rates because these are not changing. So the amount of reactant and the amount of product is not changing. And the only explanation for that is that the forward and reverse processes are undoing each other, which is the definition of equilibrium. So do you see how this represents equilibrium? Okay, now guys, let's do this. It goes way deeper than that, because when we talk about equilibrium, what we actually have is rate, K, and concentration. Because those are the things that we talk about when we talk about rate. Rate, K, and concentration. So guys, here's the question I have for you. In this silly little demonstration, and please don't say anything, but in this silly little demonstration, what represents rate, what represents K, and what represents concentration? Because all three of those things are represented here. What represents rate, what represents K, and what represents concentration? Talk about it, guys, with the person next to you. What represents which? Twenty more seconds, you guys. All right, let's pull this together. So guys, rather than ask you the question in the direction that I did, what I'm going to do is point out the things and ask you to correlate them with what we're talking about. So guys, first of all, what does the amount of water in the graduated cylinders represent? That is representative of concentration. And guys, if you're not sure why, think about this. When a reaction starts, the concentration is at a maximum. How much product do we have when a reaction starts? How much product do we have when a reaction starts? None. So we have a high concentration of reactant. We have a low concentration of product. Guys, do you remember when we graphed this stuff and we said that the amount of reactant or the product goes up and the reactant goes down, and we drew these graphs? Guys, that's exactly what we're looking at, is the amount of stuff in the tube is representative of the reactants and products. Okay, so what about this then? This one's tricky. What does this represent? K. Guys, the size of these tubes, the diameter, and I like, Matthew, that you talked about proportions. We're going to talk about that. Guys, the diameters of these tubes are representative of the K values. So this diameter, and don't get too much into the math of volume and surface area and things like that, but guys, this diameter is representative of the K forward, and this diameter is representative of the K reverse. So now, guys, we got one more to go. And I'm going to ask this the same way that I ask it of you. What is representative of rate? The water in the tubes. Guys, the rate is represented by this amount of water, the amount of water in the tubes. Now, guys, check this out. There is so much rich chemistry going on here that you could basically teach chapter 14 with these crazy little tubes. You ready, guys? Check this out. When a reaction starts, what does this amount of water represent? Concentration of the reactants. What does the diameter of the tube represent? K. So, guys, you know what this represents? Multiplication. Because K times concentration is rate. So K times concentration. Guys, all this is multiplication. I tried to figure out how to do this with the second order reactant. I couldn't figure out how to do or do exponents with this. But guys, this is literally just two tubes. Would that work? It would work. No. I think it would work. So guys, here then is the idea. So what we have here is multiplication, but now watch. And I'm just going to burn this for now. Guys, remember something that we learned. When a reaction starts, there's a lot of reactant, and it'll turn into product, but I'm just going to get rid of it. So guys, there's a lot of reactant going away. So what was representative of rate? The amount of water that I moved out of there. So guys, what is happening to the amount of water that I'm moving out of there? It's going down. Why? Because concentration is going down. But guys, didn't we say that the very first day of this unit, that reactions are always slowing down because they're consuming their reactants? Guys, that is, if you don't see how this is representative, guys, make sure you, so as we use up reactant, we are literally, the amount of water that's being transferred is less and less and less, because as this goes down, the rate goes down, and we see that reflected in the amount of water that's being transferred. Guys, wait until you get to college and your professors start teaching you about rate and equilibrium. Your brain is going to go to this day, and you're going to understand this in ways that your classmates don't. So guys, let's do this again. So filling this back up. Guys, again, in review, what does this represent? Concentration. What does this represent? K. And then when we multiply K times concentration, we get the rate. So this is the forward rate, and that's the reverse rate. And it's empty. Why is it empty? Because we don't have any products. You get it? Okay, now guys, let's watch. So what happens then when we start moving this stuff around? Well, as we move forward, we have a huge forward rate and a very slow reverse rate, 0. But now, guys, as we continue, we still have a high forward rate, but it's going down, and we learned that the first day of the unit. But guys, now we have a reverse rate. We have a small concentration times a small K value, and we end up here. And as we continue, the forward reaction is slowing down because concentration is slowing down, and the reverse reaction is speeding up because concentration of products is going up. And again, guys, forgive me about my mask. But as they are then moving back and forth, the reverse reaction is still speeding up. The forward reaction is now slowing down, continues to slow down. And eventually, where did this stop? 65-35. So guys, I'm not going to spend the, well, here, it's still going, it's still changing, right? It is hypnotic. Sometimes I really get into a groove and it gets really good. Oh my gosh, I tell you what. Okay, so guys, I think we're there. Let me just peek to be sure. Yeah, we're there. Okay, so now we're at equilibrium. So guys, now we can have a really interesting conversation about equilibrium. So guys, at equilibrium, what is equal? Is this equal? No. Guys, this is not equal, but what is this representative of? That's concentration. So we shouldn't expect these to be equal because that's not what equilibrium is about. So guys, at equilibrium, what is equal? The K values? No. At equilibrium, what's equal? The rate, which is represented by the amount of water in the tube. So now, Matthew, we're going to talk about your interesting observation. What do you know about the amount of water in these tubes? They are the same. That's the definition of equilibrium. But guys, how can that be? Well, take a look. For our forward rate law, we have a big K value and a smaller concentration. For our reverse value, we have a smaller K value, but a larger concentration, and the product of this is equal. So guys, the product of this is equal to the product of that. Does that make sense? And guys, that's where we reach equilibrium. But now let's ask an interesting question. We understand that at equilibrium, the rates are equal. What's true of the concentrations if they're not equal? They are... Yeah, but... Guys, you're thinking about it too hard. These aren't equal, but what are they? They're unchanging. So guys, link those two ideas together. At equal, and if you need, you may want to scratch this down. Guys, at equilibrium, the rates are equal, the concentrations are unchanging. At equilibrium, the rates are equal, the concentrations are unchanging. Now guys, at this point, it allows us to talk about an interesting value. And I'm going to encourage you to scratch this down with me. Guys, we are now going to talk about what are called equilibrium expressions. And I'm going to give you, you're going to want to write this down, the equilibrium expression for this process. Now guys, get used to this. Equilibrium expressions are always represented by K. Guys, at the end of the year this year, you are going to know Ka, Kb, Kw, Kc, Keq, Ksp, KFC, Kw. Did I say Kw? Guys, there's like 7 K values that you're going to learn. These are important. But guys, let me give you the K value for this. So what does C stand for? It stands for concentration. And guys, K values are always the concentration of products divided by the concentration of reactants. So this would be the K value for this reaction. Now let's look at it mathematically. 65 divided by 35. So guys, we have a mathematical value for this. Yeah, there was one other thing I was going to show you, but we'll bring this back when we talk about it later. But guys, here's the trick. That doesn't change. If we continue to do this process, that will not change. But here's then what I want you to do with this. Guys, you have all this information in front of you. Here's what I'd like you to do. I'm going to do this on a clean screen, but I'm going to reference this as if it was in front of me. So guys, here's what we've got. We've got we've got rate forward is equal to K forward times the concentration of the reactants. And then we've got rate reverse is equal to K reverse times the concentration of the products. And then guys, we've got Kc is equal to products divided by reactants. Now guys, we're going to make some interesting assumptions here. So we are going to assume that this reaction is at equilibrium. If that's true, guys, what on the board is equal at equilibrium? Rates are equal, right? So at equilibrium, this is equal to this. So guys, write this down with me. At equilibrium, rate forward is equal to rate reverse. Now guys, do this. Plug in rate forward, plug in what rate forward is equal to. For rate reverse, plug in what rate reverse is equal to. So rate forward is K forward times the concentration of reactants. Rate reverse is K reverse times the concentration of products. Now guys, do this. Solve that expression for Kc. Solve that expression for Kc. Matthew, are you done? Do you see what you just came up with? Do you see the connection? Do you? That's cool. So guys, if you're not caught up with this yet, let's solve this for Kc. So we've established that Kc is products divided by reactants. So if I want to get this to products divided by reactants, I'm going to divide both sides by reactants. So concentration of products divided by concentration of reactants. But then I need to divide both sides by the K value of the reverse. And I end up with this. So guys, you ready for the deep thought? Why did this stop at a 65-35 ratio? Because that's also the ratio of the diameters of these tubes, with the understanding that it's not clearly a linear relationship because volume is the square of the radius. But guys, that 65-35 ratio that we see here is also reflected in this ratio. That this 65-35 ratio by concentration is also represented in the 65-35 ratio that you see here. Guys, with that said, grab your books and open up to the first page of chapter 15. So guys, turning to page 613. You'll notice at the top of page 613, we have a simple equilibrium process where dinitrogen tetroxide turns into nitrogen dioxide, 2 of them, and that's reversible. You'll notice down below, they write the rate laws for the forward and reverse reactions. And then assuming that these processes come to equilibrium, they establish the same relationships that we have on the board. The product divided by reactant ratio, which is the NO2 squared, which we'll talk about in a minute, divided by the N2O4, is equal to the K ratios of the forward and reverse reactions, which is equal to a constant, and you now understand that that constant is termed Kc. Because everything that we just did relative to this silly blue food coloring water is exactly bared out in this representation that they give relative to this reaction of nitrogen oxide compounds. So guys, while this is silly relative to just us passing water around, it is an amazingly solid representation of what actually happens chemically, not only in terms of visualizing it, but also generating math that describes these processes. Questions or things you want to talk about relative to this? Stay on task, buddy. Doesn't matter. We okay? Are we good? Okay. So guys, what I'd like to share with you then, as wrap this up, is I'd like to make sure you guys are all comfortable with this, and where we're going to stop. So guys, make sure that this is okay with you. And this is where we're going to wrap up today. So guys, what we have here is a graphical look at the same simple equilibrium process. Notice that in both graphs, time is on the x-axis. So now guys, looking at concentration, let me ask you, which is our reactant, A or B? A is our reactant because we start with some. B is our product because we don't start with any. And then guys, you'll notice that they draw a line that represents where this thing reaches equilibrium. So guys, when this thing reaches equilibrium, notice what happens to the concentration. How do we describe what happens to concentration? They become unchanging or constant. Guys, that's what we see here with our 65-35 ratio. When the process reaches equilibrium, the concentrations become constant. Notice over here that when a reaction reaches equilibrium, the rates not only become constant, they become the same. And these are related. These equal rates cause this exchange to happen in an offsetting way, and that's why the concentrations become equal. Does that make sense? Okay. So, guys, I think that is probably going to be, that's going to be our safe. Well, how much time do we have left? We're going to do one more thing. Guys, the last thing that I want to talk with you about is this. Ready? So, is it 65-35? Okay, imagine that we do this. Imagine that we start with all product and no reactant. Again, same tubes. Big tube forward, small tube reverse. Guys, if we start with all product and no reactant, what's going to happen if I do this? So as I continue, the forward reaction now has a rate. The reverse reaction is slowing down. The forward reaction is speeding up. And guys, without spending all the time to do this, you want to hazard a guess where this is headed? To the same equilibrium. Guys, it is headed back to 65-35. That ratio is truly a constant. Guys, ready for a deep thought? What would we have to change in order to change that 65-35 ratio? The values of K. And what did we learn last time changes the values of K? Surface area, temperature, things like that, huh? Right. So guys, the idea is that this will settle back into the 65-35 ratio. And guys, the bottom line is this. It doesn't matter where we start. All and none, none and all, 50-50 of each. It doesn't matter. These reactions will always go to the same equilibrium ratios. Guys, so much so that you can look up these values in a book. This book actually has the Kc values for every typical reaction ever carried out. Of course, they're temperature sensitive, but guys, you can look up all these Kc values. They are literally constants. So, yeah. Oh my gosh, you just wait. You wait till, it should be next time, but it won't. This is the craziest, most fascinating, the labs. There's all sorts of awesome stuff that we're going to do with this, specifically acids and bases, but it's fascinating. So guys, let's make sure you're okay with this, and then we're going to wrap it up. Let this soak in for a second. Guys, this is what is called the Haber process. The Haber process is the synthesis of ammonia from nitrogen and hydrogen gases. Some people would say this won the war for us, World War II, because all of our soldiers were overseas and there was nobody back here to farm, and we needed to grow more food more easily, and we needed fertilizer. And Haber actually figured out how to synthesize ammonia, which is fertilizer, from the elemental gases nitrogen and hydrogen. But guys, take a look at the graphs down below. Hold on, Spencer. Hold on, buddy. Hold on. So guys, down here, over time, notice what's happening. So as the reaction takes place, you'll notice that NH3 is our product. You'll notice that N2 and H2 are our reactants. When these reach equilibrium, notice the representative concentration ratios. Well, guys, how is the trial on the right different? It's the reverse. Here, we started with no reactant and all product. But guys, you'll notice they come to exactly the same equilibrium concentrations. It does not matter what direction we come at these things. We always end up at the same ratios. Just one second. You guys okay? Okay. So guys, let's do this. Do what of these... Oops, just a second. Do what of these you can. And while we're writing these down, Spencer, what did you want to talk about? So what they do is they actually dissolve it in water. And when they dissolve it in water, you end up with ammonium hydroxide, and they actually spread that out on the fields, and it creates free nitrogen that the plants need in order to grow. So guys, again, we're going to do what of these we can. When we're done, we will regroup and we will finish up what should have been today's material. And then we are going to get into the math of this, the time following. Then guys, following that, we're going to talk about Le Chatelier's principle, and then we're done with this unit.